Hello, my name is Denisa Mcdonald, and I'm a PhD student in computer science at Drexel University. Today, I'm presenting our work, Knitted Sensors, Designs and Novel Approaches for Real-Time, Real-World Sensing. This work extends the capabilities of knitted sensors, which rely on one conductive carbon-coated yarn and two external connections. The sensor depicted in Figure 1 is produced in one piece during digital knitting, with minimal post-processing. It's very thin, stretchable, and behaves like fabric. Figure 2 illustrates the scalability of this process. Wires can be connected at the two yarn endpoints. The fact that there are only two connection points makes both manufacturing and system integration easier. Additionally, it reduces the risk of breaking contact at connection points, making the sensor more usable and robust. However, the minimalism of the system also means that there is reduced information output from it, shifting the burden of complexity to more refined sensing and computational models. In this work, we discuss moving the sensor technology closer to the real world. Contributions include building a recognition model to identify precise location of touch on an existing knitted sensor, building a real-time signal processing and acquisition circuit, conducting user studies to evaluate the model and investigate its robustness in the real world, and introducing several design prototypes of knitted sensors constructed through the same knitting process. We propose a system which is composed of several connected components. The knitted textile sensor with 36 locations of touch along the same conductive yarn, a real-time sensoring microprocessor, and a recognition model. It has a feature constructor step and a neural network which identifies location of touch. The recognition model, once trained for eye accuracy, can in the future be embedded into a dedicated microprocessor or handheld device and connect to the sensing microprocessor to identify location of touch in real time. In the next slides, we're going to be looking at these components individually. The microprocessor inputs a signal into the system and processes it through Bode analysis. There are 96 frequencies used outside of the range of electromagnetic interference, or EMI. The plots on the top show the system response in the absence of EMI. The input signal is depicted in black, while the outputs from either yarn endpoint in red and blue. The bottom plots illustrate data captured in the presence of EMI. From the first plot, we can see that the output is distorted during EMI exposure. However, the second one shows that the EMI frequency range can be discarded and the signal can be reconstructed based only on the desired input frequency range. So each sensor touch event consists of 250 temporally related measurements of the voltage gain values captured as explained. Statistics are then computed on the frequency values for each step for a more stable representation. Additionally, to retain the most relevant information only, we subtract a baseline representation of the system, which is its state with no touch occurring. The next component of the system is the neural network architecture. It is composed of 3 layers of the long short-term memory cells, which have been widely used for sequential data analysis, including time series data, since they capture temporal dependencies. The input into the network is a touch event, represented as the sequence of statistics on the gain values computed above, and the output is one of the 36 locations on the knitted sensor. This model, in order to properly recognize location of touch, needs to be trained with user data, which we'll collect through our user study described next. In order to move toward real-time, real-world knitted sensors, we conducted a series of user studies. The first study enables the creation of a robust location detection model. The second demonstrates its generalizability with new users. And the third study investigates its robustness to potential sources of distortion. It's divided into 2 smaller studies. In one, the sensor was exposed to electromagnetic radiation, and in the other, the sensor was stretched while the data was being collected. Here are the results of those studies together with their classification matrices. The data from the first study, which was used for training through 5-fold cross-validation, produced an accuracy of 58% for location detection. Training happened with 386 samples per class, which is a limited number for deep learning algorithms to perform well. Through the model evaluation study, we obtained an accuracy of 66%. Our robustness test report results of 80% accuracy for EMI exposure and 30% for stretching. Chance accuracy is 3% since there are 36 classes. These results are subject independent in order to remove the need for individual calibration. In the future, training should include a variety of conditions and more data for results to improve. Using the same manufacturing process, we can produce a variety of needed design forms that rely on one conductive yarn combined with regular yarns and two external connections. The sensors illustrated here are some examples and include a piano keyboard, volume controller, media control buttons, as well as larger pad for different designs. These sensors can be connected to the same signal processing hardware and rely on the same neural network architecture, but each model needs to be trained with new user data that is specific to the sensor geometry. The technical contributions and studies conducted in this work helped us lay the foundation to advancing toward viable, robust, knitted textile touch interfaces. For more information, please refer to our paper or contact us. Thanks for listening.